Okay, so what do you do with the sun at different declinations? Well, say you're in the northern hemisphere, somewhere up there. Now, what your sextant is going to read is this angle right here, because that's the angle between your zenith and where the sun is. So what you're going to do to find your latitude, you're going to add your sextant reading to the declination. What happens instead if the sun's down here? All right. Now your declination is in this direction, and your zenith angle is going to be all the way down to here. So it's going to be much higher than your latitude degrees. So what you would have to do is you would have to subtract the declination from your sextant reading to get the angle between you and the equator, which is your latitude. Now, there's two other situations that you can have. First is that the sun is directly over the equator, in which case the declination is 0. It doesn't matter if you add it or subtract it. You don't even have to deal with it. The other one is, what about those situations where you're down in the tropics and the sun, the declination of the sun, is actually further away from the equator than you are? In that case, what you would do is reverse this. You would take the declination minus your reading would equal your latitude. When you're doing this, first of all, you kind of know more or less where you are in the world. I mean, there's a big difference between Hudson Bay and the Bahamas. All right? So you're not going to really confuse the Arctic and the tropics. So chances are you would be in the tropics somewhere if the sun was north of you, or if you were in the southern hemisphere if it was south of you, which is this situation. So you would realize that. And what you would do is basically make the correction for it. You look where the declination of the sun is, you realize that you're closer to the equator than the declination of the sun. And that's when you have to adjust your sextant reading. But if only it was that easy. There's another problem that you run into, and that is what you read with your sextant is called HS. However, you have to make some corrections to that to get the usable angle, which is HO. Now let's go ahead and go through some of those corrections. The first one has to do with the sextant itself. When you have it set for 0 degrees, 0.0 minutes, these optical lines should be exactly parallel. So in other words, if you look through the telescope at a star, for example, you will see one point of light. Well, sometimes you get a situation that looks like this. I'm going to use the split mirror just to make it easy. You have a horizon over here, and then that's the reflected horizon, and your visual horizon is there. They don't match up. This is called an index error. And that is a mechanical error in the sextant. Now, there are two ways that you can fix that. One is that you adjust this mirror so that those two line up. The other one is that you simply dial in whatever number needs to be made in order to make those two line up so that they're square, like this. And then what you do is you record that number, and that's the index error of your sextant. Generally, they're pretty small. They say that you can ignore it if it's less than 5 minutes. I'm an internal medicine doctor. I can't ignore anything, not one little thing. So I'll either adjust the sextant so my index error is 0, or I'll simply record that 5-minute error and I'll apply it to my calculations. We're going to do that when we talk about actually doing a sextant reading on Friday. Today we're looking at basically the mathematics of the sextant reading. So let's look at the errors that we actually have to correct for based on how a sextant works, not just simply the mechanics of the sextant itself. So first of all, the sextant works by comparing a tangent line at a point on the Earth to an angle. So you read this angle, and from that you calculate the angle that you want to use, which is this one. However, in order to do that, we would have to be up to our eyeballs in the water, reading straight out. We never do that. We're either standing on the shore as I was, or you're on the deck of a ship and you may be 100 feet above the surface of the ocean. So what you're going to have is this situation. You're going to be up here. You're going to read your angle out to your object, and then you're going to read the angle down to the horizon. What you want to do is find your horizontal and measure this angle. This is extra, and that is called dip. Okay, so what we do now is we go back to the Nautical Almanac and we go down to this section that says sun. This is where you'll find the correction data for your sun sights. And the very first thing, dip. So if you're right on sea level, your dip angle is 0. However, if you're 5 meters above the sea, you're going to have to subtract 4 minutes from your sextant reading in order to get an accurate angle to the sun from your horizontal at your height above the sea. Okay, so let's look at another error that we have to take into account, and that is the error of refraction. Now, one of the things that we know is that when light enters our atmosphere, it is bent. And as we look up with our sextant, we will think that the sun is up there, when in reality it's lower, it's down here. So how do we correct for that? Well, we go back to the Naval Almanac. Oh, by the way, I think I made a slight mistake there. This table for dip and such is related to a star. The sun is over here. And once again, it's still minus 4 minutes, but I want to use the correct table. But right here is our refraction table. And our refraction table has to do with what our measured altitude on the sextant is. So between 15 degrees 16 minutes and 15 degrees 41 minutes, so we're going to have to subtract 3.4 or 3.3 minutes of angle, depending on where our reading is, whether it's closer to 15 degrees 16 minutes or 15 degrees 41. And that takes into account this error right here. So here's our dip error, here is our refraction error. Now here's the other problem that we run into, and that is our angles have to be to the center of the sun. However, it's very difficult to get a sextant reading to the center of the sun. Generally, what you're going to do is you're going to have your horizon here, and then you're going to have the sun sitting right on the horizon. So what we do is we measure to what they call the lower limb of the sun. What we want to know is where the center of the sun is. Now that distance that you have to correct is called a semi-diameter because it's half the diameter of the sun. And there are values for measuring from the lower limb of the sun, or sometimes you'll measure from the upper limb of the sun. There are different values, and those values change throughout the year as the distance from the Earth to the sun changes as we orbit. Now let's go back to the Naval Almanac and have a look at that. So here are the semi-diameter corrections. Now I did my reading to the lower limb of the sun, and I did it in August. So I have to add 15.8 minutes to my sextant reading. Now that 15.8 minutes fixes the error that I had right here. Let's just kind of review this. Our raw reading is HS. That's the raw reading off the sextant. What we want to find is the corrected reading, which is HO. So the first thing that we do is we fix the index error. Then what we do is we correct for dip, refraction, and semi-diameter. And once we've corrected for those, always doing index error first, we come up with HO. Clear as mud, right? But actually, it's really not all that difficult. It took me probably 3 or 4 days to get good enough with the sextant to actually be able to get my reading within 1.8 nautical miles. And quite frankly, I'm quite proud of that, because most sextant readings, if you're within 10 or 15 miles, you can see where the island is and just kind of steer towards the island. It's got to get you close enough to at least see where you're going, all right? You don't want to have a sextant reading that says you've arrived and have nothing but clear ocean around you in all directions. You have to get a little closer than that. And with a little bit of practice, you can easily do that. Now, this Davis Mark 25 sextant is a very good entry-level sextant. It's about $250. It's really not all that expensive. It's made out of plastic, it doesn't rust, it's very durable, and it's extremely easy to use. There's even a little button on the handle right here that lights up where your readings are. It also comes with some really good books. Okay, so today we talked about the basic operation of the Davis Mark 25 marine sextant. Now in our next episode, I'm going to talk about how do we use the sextant if we don't have access to a water horizon. How do we do it in a landlocked area? Well, Lewis and Clark actually carried a bowl and some mercury with them for that, using what's called an artificial horizon. In our next episode, we're going to talk about how we can do that here and how I've done it on a number of occasions. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. I hope you found this enjoyable. Remember to hit that like and subscribe on your way out. Take care, guys.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.